तो इश्यूज है, मैं बता दूं तुम्हें जो क्लासेस इस वाली जो क्लास के नोट्स प्लान की वीडियोस आई हैं, एक दो चीजें मैं पूछना चाह रही थी।
यस
तो
मैम,
चलाई,
बोलिए आप।
एक उन्होंने बोला था कि इन लैडर ऑपरेटर्स द आइगन वैल्यू लैम्डा शुड बी एन इंटीजर।
यस।
इसका फिजिकली कैन यू जस्ट मैथमेटिकली शी हैज प्रूव्ड, बट कैन यू गिव सम फिजिकल इंसाइट इनटू दिस?
Okay,
नंबर वन,
so yeah, yeah,
नंबर
yeah. Mm-hmm.
eigen feats of the A and A dagger operator.
Yeah.
And number three, a particular equation is being used that psi n x is equal to bra of x into cat of n.
Okay.
So can you explain how this is coming and how to derive the expression for psi n x using bra of x, cat of n?
Cat off.
N is a number.
Ah, okay. A number operator.
Yeah, number.
Okay.
इनफैक्ट पता है
Okay.
कि ये वाले जो नोट्स, लाइक दीज वीडियोस आर रिलीज यस्टरडे ओनली, फ्राइडे।
Ah,
तो
okay.
आप आते हैं ना, ये उसी वीडियो को लेके आते हैं।
Hmm. Ma'am, what you can do if you are feeling that they are releasing the videos late, I think they are already there on YouTube.
या आई एम डूइंग दैट ओनली, आई एम डूइंग दैट
Yeah.
ओनली, सो आई एम जस्ट गोइंग थ्रू दोस वीडियोस
Yes.
ड्यूरिंग द वीक। ड्यूरिंग द वीक,
Yes, ma'am. So,
या दिस इज व्हाट आई एम डूइंग।
so that is one thing.
या
Okay. Secondly, yeah, we can discuss all these things. I think couple of things we can discuss now only. Won't take much time. So one thing is why this uh, ladder operators, they should have an integer value, eigenvalues, right?
या
Okay, so I'll try my best to give you some physical intuition. So one thing is, okay, let's first consider why they are called a ladder operator. So we have a ladder like this, right? Like this is, for
यस।
example, our ladder. Now, in terms of a system, so the steps of these ladders, they are the possible states, right? So these steps, for example, these steps, they denote states of a particle, particularly for a simple harmonic oscillator, for let's say for time being,
या
right? So when we when we plot these states, if you remember the energy, that is given as n plus half h cut omega, right?
या
Where n goes from 0, 1, 2, so on, right? Which means, okay, let's say the E01 will be just half h cut omega. For E1, we'll add h cut omega to this thing, right? And then we'll go on adding this h cut omega term again and again.
या
So if you want to go from any state, let's say this is your nth state, this one, to n plus 1 state, right? So what do you want to do? You want to jump up in terms of energy by h cut omega, right? So which means that all these steps, they are equidistant from each other. Doesn't matter which energy state you are in. If you add h cut omega, you will end up in the next state. If you take
या
out h cut omega, you will go to the previous state. Okay. So therefore, what we are doing, we are going either plus h cut omega or minus h cut omega, right? So essentially, what these ladder operators are doing, for example, if you consider the raising operator, a dagger, it will take you from n to n plus 1, right?
या
And because this state has to be an integral multiple of h cut omega, therefore its eigenvalue has to be an integer. Because if it is some fraction of h cut omega, you will end up, let's say, somewhere in between here, which does not correspond to any physical state of the system.
Okay.
Okay, so we get the physical states of the system only when we move up by some integer value of h cut omega or move down by some integer value of h cut omega. That is when we are at these states, so-called states.
Mhm.
So
Can
yeah,
we somehow have a continuum of, sorry, can
sorry.
we somehow have a
Hmm.
continuum of these states?
So in quantum mechanics, no, but okay. Let's do one thing. So what will be our delta E? So let's say this is En and then we have En plus 1. So what is our delta E? So delta E is simply h cut omega, right?
Mm-hmm.
For a continuous states, this delta E should tend to 0. Correct?
Mm. Yeah.
So when can we take this limit? So classically we can take this limit because this h cut is very small, right? It's already 10 to the minus 34.
Yeah.
For a particle whose wavelength, the de Broglie wavelength, is much smaller, right, compared to its size,
Okay.
then we can take this limit that delta is 0 and then we can consider this to be a continuum. But when we have a quantum particle, like an electron for example,
Mm-hmm.
where the size of the electron and its corresponding de Broglie wavelength, they are of comparable nature, then this limit does not hold, right? This no longer works. This h tends to 0 basically takes you to classical mechanics.
Okay.
And this limit you can only take when your de Broglie wavelength and the size of the particle that is under consideration, they are drastically different.
Okay.
That's why we don't see these quantum states uh, in our day-to-day life, because
Hmm.
most of the particles that are there, they are like classical particles that we experience with our own eyes, because
Hmm.
there this limit is pretty accurate, right? So
Hmm.
the systems behave classically. But if we go into as we go down to smaller and smaller particles, then we have to consider all these effects, and then this quantization comes in, right? Because these states become quantized. Classically, we don't talk about quantized states. Classically, all the energies are possible.
Yeah.
Yeah,
Actually, this harmonic oscillator problem, I find it so powerful.
it
Then
is.
any problem can be reduced to harmonic oscillator problem.
Yes.
So, if,
In fact, if you study field theories like quantum field theories,
mm-hmm.
they build upon this harmonic oscillator problem, and then
Mm-hmm.
just they from this single particle which is quantum oscillator, they build a
Mm-hmm.
field out of this, and then
Mm-hmm.
instead of exciting a particle, they excite the field, and then they
Mm-hmm.
see that the particles are emerging because of field excitations. For example, if you take an electromagnetic field, the excitation of an electromagnetic field will give you a photon,
Yeah.
right? So you
Mm-hmm.
are absolutely correct. The quantum this oscillator is like a brick, and you can build
Backbone. Like a
like,
backbone.
yes,
Backbone of
exactly.
the universe.
Yeah, yeah, yeah.
I can we compare it with the Fourier series? For example, any function can be decomposed into its Fourier series consisting of cos and sine. So
Mm-hmm.
every cos and sine is a oscillator. It's an
Yeah.
oscillation. So we get Fourier series when the function is periodic.
Yes.
Then there's the summation. But when the periodicity breaks and the function becomes aperiodic, then we go to the integral, which is
Yes.
the Fourier transform.
Yes.
Right? So there is a transition. There we have a transition from the summation to integration.
Exactly.
Is there any analog to this? That this is a summation, harmonic
Uh,
oscillator is a
I
summation.
okay. The one analog that I can think of is that when we go from particles to fields, then this summation changes from sorry, then this changes the summation to integrals, right?
Okay.
Because when you have particles, if you want to write the total energy, what we do, we just add the energy for all the individual particles, and we get some state of the particles, which is like a summation. But when we write it in terms of fields, then
Mm-hmm.
it's more like a continuum and
Okay.
not like discrete individual particles.
Okay.
So in that sense, your analogy is 100% correct.
Okay.
Yeah.
Thank you.
Okay. Okay, so you had couple more doubts. I think we can discuss them later
Okay.
after the class.
Yes. Sure. Thank you.
Yeah, okay. So I think few people have already joined. So before I begin, quickly, if anyone wants to ask anything. Okay, no problem. So let's solve few problems based on the material discussed for this week. And for the first problem, we are asked to write the Heisenberg equation of motion here. Okay, the Heisenberg equation of motion for the time dependent spin operator S of x. Okay, so note that we are asked about S of x. And what are we given? We are given that we have one Hamiltonian due to interaction of a particle m, charge q, and spin s with a magnetic field along the z axis. So this is our Hamiltonian. Let me write down the Hamiltonian. It is minus qb by mc s of z. Yeah. So also notice in the last line they have written that this value minus qb by mc is equal to some omega. So we can simply write this Hamiltonian as omega times s of z. Okay. Now what we want to do, we want to write the Heisenberg equation of motion for the time dependent spin operator Sx of t. So we want to write the equation of motion for Sx of t. For now we know that for any operator, let's say any operator A, for any operator A, the time evolution is given by dA dt is equals to iota by h cut and h comma a. Correct? This is what we have. So instead of a, here we have s of x. So our equation becomes d, sorry, yeah. So d s of x dt, that is iota by h cut. Okay, so instead of h we can write omega s of z, and instead of a we can write s of x. So let's take omega outside. This becomes iota omega by h cut, commutator of sz and sx. Now in the previous class we didn't know these values, but I hope now we are comfortable with spins and angular momentums. So we know that this, using this cyclic relation, this the value of this commutator will come out to be iota h cut times sy. Correct? So this is z, x and y. So this becomes iota omega by h cut, and this commutator gives us iota h cut s of y, right? So this h cut will cancel out, and this iota square will become minus 1. So we'll have minus omega s of y. So finally, our equation of motion becomes dsx dt is equals to minus omega times s of y. Okay, which is option B.
Sir, in the first line, you took minus QB by MC SZ equal to omega SZ.
Yes.
But I thought QB by MC was omega, but we ignored the sign.
Here, because in the question they have explicitly mentioned that this omega has a minus sign.
Okay, right.
Yeah, because it's
Yeah.
mentioned explicitly. That's why we considered the minus sign in omega itself. Otherwise, you are correct. Omega is generally QB by MC.
Okay, sir.
Yeah. Okay. Anyway, if you didn't consider this minus sign, I think the this equation will remain the same. The option B will remain the same, right? Because that minus will appear anyhow. Okay. Okay.
Right, sir.
Okay. Okay. So let's come to second problem. I hope there are no doubts in first problem. Okay. So for second problem, we are given that we have two non-interacting angular momenta. Okay, J1 and J2. So they are non-interacting. The okay, and the question is then which of the following commutation relations are correct? Okay, and the total angular momentum is just the addition of these two individual angular momentum. Okay, so first of all, let's calculate the first operator, sorry, this first commutator, which is jx comma jy. Now I can write jx as j1x plus j2x and jy as j1y plus j2y, right? And then we can separate them out. So this expanding, we can expand it, and we can write this as j1x comma j1y plus j2x comma j2y, and then we'll have cross terms j1x comma j2y, and lastly we will have j2x comma j1y. Okay, now we are given one very important things, that these two angular momenta, they are non-interacting, and since they are non-interacting, so these two terms, because this has the first term is the x component of the angular momentum j1, and this is the y component of angular momentum j2, because 1 and 2 are non-interacting, so this commutator goes to 0. Similarly here we have j2 and this is j1, so this commutator also goes to 0. But here the first commutator has j1x and j1y, which corresponds to angular momentum j1, and here similarly it corresponds to angular momentum j2, so they will not go to 0. Instead, because we know the cyclic relation, so this is x and y, so what we will have? We will have iota h cut j1 z. right? Similarly here, this is again x and y, so we'll have iota h cut j2 z. Okay, so we can take this outside, we can write j1z plus j2z, and we know that j1 plus j2 is total j, so we can write it simply as iota h cut times jz. Okay, so if we look at our option A, there's an additional minus sign that is coming, right? We have iota h cut jz and they have minus iota h cut jz. So this in fact is not correct. Okay. Similarly, if we change x to y, y to z, we can show that, okay, if I change this x to y and y to z, what will we get? Because of this cyclic relationship, we know that we will get iota h cut times jx. Again, there is an additional minus sign which is coming here, so this is also incorrect. You can solve it explicitly like we have done for the first one, and you will get the same thing. For time being, I am not going to repeat the same calculation. Just change x to y and y to z, and you will get the same relation. Okay. Now let's look at part C and D. Here we have j square instead of x and y. Okay, and it is given that j square is the total angular momentum. Okay, so let's check for option C where we have j square comma j1 square. So the commutator j squared comma j1 squared, we can write this as j1 plus j2 squared comma j1 squared, right? Because this total angular momentum j is nothing but j1 plus j2 as given in the problem here. J is j1 plus j2. Okay, so let's open this thing up. What will we have? We'll have j1 squared plus j2 squared plus j1 j2 plus j2 j1 and comma j1 squared, right? Okay, so firstly we will have this term j1 squared comma j1 squared, yeah. Then we will have j2 squared comma j1 squared, and then we will have couple more terms j1 j2 comma j1 squared plus j2 j1 comma j1 squared. Okay, so we'll have these four terms. Okay, so now this first term will go to 0, right? Because we have j1 squared and j1 squared. So this first term, this goes to 0. Now here we have j2 squared and j1 squared. We know that j1 and j2 are non-interacting. So this goes to 0. Yeah. Similarly, what we can do for this third term and the fourth term, we can again expand this. So j1 will come outside, and inside we will have j2 comma j1 square. So that term will go to 0. Okay, let me write this down explicitly. So this term, this will be j1 j2 comma j1 squared plus j1 comma j1 squared j2, right? So again you can see that j2 and j1 are non-interacting, so this goes to 0. And here you have j1 and j1 squared, so this term also goes to 0. So this entire term goes to 0. And similarly, this last term will also go to 0. I can again expand this in similar fashion. So essentially all 4 terms are going to 0. So what we can do is we can write j squared comma j1 squared is equals to 0. So option C is correct. What about option D? For option D we have j2 squared instead of j1 squared. So we have j squared comma j2 squared. So will this be 0 or will this not equal to 0? What do you think? We have done the same exercise for j1 here.
Zero. It will be zero.
It will be 0. Yes, you are correct. Because there is no difference as such between j1 and j2. If the square of total angular momentum j is commuting with j1 square, then it should also commute with j2 square. If you want, you can check it explicitly. The calculation remains the same. But I'll, for sake of time, I'll just leave it here. And this is also correct. Okay, so I have solved part A and part C. And part B and part D, I have just said that they follow from our previous calculations. However, I suggest that later sometimes you go back and give it a try and you'll get the same answers. Okay, any doubts? Should we move on?
Hmm.
Okay, move on. Move on, please.
Okay, good. Let's go on to the next problem. So we are given a wave function psi, okay, and this is written in terms of two more wave functions, psi n1 l1 m1 and psi n2 l2 m2, okay, which is a combination of normalized stationary state hydrogen like wave functions. Okay, so we are given that these psi n l m, they are normalized stationary state hydrogen like wave functions. Okay, basically they are orthonormal because they are hydrogen like, so they are normalized but they are also orthogonal to each other, which means that they are orthonormal. Okay, and then they are asking that for the given wave function, which is written as a linear combination of these two, for psi to be normalized, c1 and c2 must satisfy the condition mod c1 square plus mod, okay, I think this there is a typo here. I think this should be mod c2 square, right? So mod c1 square plus mod c2 square is equals to 1. So true or false? Okay, obviously we know it's true, but let's prove this thing. So the wave function that we are given psi, which is a function of r, theta and phi, it is written as c1 psi n1 l1 m1 plus c2 psi n2 l2 m2. Okay, so if we want this to be normalized, they have given psi to be normalized. What is the normalization condition? That this thing equals to 1. Yeah. So if we write the Bra and Ket notation of psi, what will we get? We will get c1 psi n1 l1 m1 plus c2 psi n2 l2 m2 c1 psi n1 l1 m1 and c2 psi n2 l2 m2. We'll get this thing equals to 1, right? Is that clear? Okay, let me put brackets. Okay, so what will we have then? Okay. So because this is in the bra space, this first term, right? This first term is in the bra space, and the second term is in the ket space. So if I take out this coefficient c, here it will become c1 star, right? And here I'll have psi n1 l1 m1, and this c1 is in ket space, so it will remain c1. So I'll have one c1 here, and we'll have psi n1 l1 m1. So this is one term that we'll get total 4 terms. The second term that we'll get will be c1 star, c2, and then this psi n1 l1 m1, and psi n2 l2 m2, correct? Then we'll get c2 star, c1, psi n2 l2 m2, psi n1 l1 m1, and finally c2 star, c2, psi n2 l2 m2, psi n2 l2 m2, and this has to be equals to 1 for our normalization condition to hold true. Okay, so now we have these 4 terms. So what will happen to this term?
Second and third term will be 0 because they are orthogonal.
Correct. This goes to 0, this goes to 0. What about this first and the fourth term?
Normal wave function, this is 1 and this is also 1.
Yes, because it is given that they are normalized. So this term goes to 1 and this term goes to 1. Okay. Good. And how can we write this thing? C1 star times C1?
Mod C1 square.
Exactly. So this becomes mod C1 squared, and this becomes mod C2 squared. Other terms are 0, right? And this is equals to 1. And this is the same thing that is given to us. So the answer is true. So for psi to be normalized, this condition must be satisfied, that the coefficients, the square of the mod of the coefficients should equal to 1. Okay. Any doubts here? No? Okay, good. Okay, so moving on. Okay, this we have similar kind of problems we have done earlier, where we found out the expectation values of the energy. Only difference is that here we now have a hydrogen atom. Okay, so it should be a simple problem. Let's see how to tackle this one. Okay, what we are given? We are given at time t equal to 0 that our hydrogen atom has this wave function. Okay, so this is the wave function of the hydrogen atom given to us. What do we notice about the wave function? That this first of all, the subscripts are the values of quantum numbers n, l, m. So this is, here n is 1, here n is 2, n is 2, and n is 2, and then l is 0, and so on, right? So just looking at the wave function, we can tell what are the values of the quantum numbers. Then the question asks, what will be the expectation value of the energy of the system? Okay, and the answer is given in terms of E1 and E2, and which is written at E1 and E2 are the energies of the first and second states respectively. Okay, so first thing, we have 3 quantum numbers. We are n, we have l, and we have m. And we are asked about the expectation value of the energy of the system, and the system is a hydrogen atom. So on which of these quantum numbers will our energy depend?
I think n, right?
Only n, yeah, correct. So we have to worry only about n. We don't care what the value of L and M are for this particular problem. Okay, so the first term you can see that corresponds to n is equals to 1, and remaining 3 corresponds to n is equals to 2, right? Yeah. Okay, so okay, so this is our wave function, and let's say these are our coefficients c1, c2, c3, c4, and so on. Okay, let me write them explicitly: c1, c2, c3, c4. Okay, and notice that we also have 1 by root 10 outside, so our c1 will be 2 by root 10, right, which implies mod c1 squared will be 4 over 10. Okay, similarly c2 is 1 by root 10, which implies mod c2 squared is 1 over 10. For c3 we'll have root 2 over root 10, sorry, root 2 over root 10, which implies mod c3 squared is 2 over 10. And for c4 we have root 3 over root 10, right? Yeah, root 3 over root 10, which implies mod c4 squared is 3 over 10. Now to quickly check, one thing that we can quickly check, that if we add all these we should get 1. So 4 plus 1 5, and this 7 and 10, so we are getting 10 over 10, which is 1. So our wave function is normalized. Okay, we have to always check if our wave function is normalized or not. Only then we can write our expectation value of energy. Okay, so okay, let me write it down explicitly. So the expectation value of energy E is given like this: psi h psi divided by psi. Okay, and this we have already checked that our wave function is normalized, so the denominator just goes to 1, and what we are left with, we are left with simply this thing. Okay, but we have already computed the mod of the coefficients, right, the mod square of the coefficients, so we can just forget about this thing. And what we can do is we can write the expectation value of energy E as summation of over all the states mod Cn squared times En for all n, right? Because this mod Cn square, this gives us the probability that the particle will be in that state, right? And En gives us the corresponding energy of that particular state. So we multiply the energy of the state with its corresponding probability, and then we add all of them up. That will give us the expectation value of the energy. So as we noticed earlier, the last 3 states correspond for n is equals to 2, and the first one corresponds to n is equals to 1. So what we can do is we can expand this thing as mod c1 squared times e1 plus, here we'll have all these things: c2 squared, c3 squared, c4 squared, yeah, and this multiplied by e2. Okay, so this is mod c1 square is 4 by 10, so this is 4 by 10 e1, and then let's add all these up. So this will be 1 plus 2 plus 3, which is 6, so 6 by 10 e2. So cancel out 2 by 5, cancel out 3 by 5. So this is 2 by 5 e1 plus 3 by 5 e2. This is the expectation energy in terms of e1 and e2. Okay, So I think option C. No, option D. C has a minus sign, D has a positive sign. Okay. Any doubts in this one? Okay. I hope all of us are comfortable with this relation. Okay. If not, we can derive it in the end of the lecture. Just let me know. Okay. It's simple two-step derivation.
Yeah, please derive it, huh? Please derive it at the end of the session.
Okay. Okay. Just remind me if I forget. Okay. So let's move on for the time being. We have the gets j comma m, which are the simultaneous eigengets of total angular momentum operator j square and its j component jz. Okay, which is very standard way of representing j comma m, right? And we also know that the eigenvalues are j times j plus 1 h cut square and m h cut respectively. This is like our hydrogen atom problem. Then the question is that this operator j plus acting on j comma m and this operator j minus acting on j comma m, they are also eigengets of j square with same eigenvalue. Is this statement true or is this statement false? Okay. So j plus and j minus, they are ladder operators, right? Ladder operators. And for ladder operators, we know that the commutation relation holds true. So their commutator is 0.
Sir, what is ladder operator?
Okay. So a ladder operator. Hmm. So do you know about harmonic oscillator?
Yes, yes.
Okay, good. So for a harmonic oscillator, let me write for simple harmonic oscillator. The energies, they are written as n plus half h cut omega, correct?
Correct.
Yeah. So the ground state energy is this one. The
Right.
first excited state energy will be this energy plus h cut omega. Second one will be plus 2h cut omega and so on, right?
Yeah.
So let's say this is my ground state, okay, and this is absolute zero energy. So this has energy of half h cut omega, correct? Now if I want to go to my first excited state, I need to go up by h cut omega more energy, right?
Right.
If I want to go to the next excited state, again I need
H
h cut
cutting.
omega, and I can keep on going same, right?
Right.
So this energy states where we have this constant kind of a difference between two states, they form this ladder kind of a structure, right? You can see that we have these steps
Okay.
which are equidistant from each other. Now let's say I am at some time, random time, I am sitting in this position, okay?
Yeah.
So
Okay.
if I want to go to the next state, right? If I want to go to the higher state here, for that we have a ladder operator called, generally written as a plus, If I want to go down one state, I have an operator called a minus. So these a plus minus, they are called ladder operators. So let's say this is some state of my wave function, which I can write, let's say, as n. Okay, this is the nth state. If I do raising operator, the raising ladder operator, what I'll get? I'll go to n plus 1 state. Okay, and there will be a normalization factor under root n plus 1, which I am not writing for timing. But if I if I operate with a lowering operator on this nth state, I'll come one state below. Okay.
Okay.
So you can think of these ladder operators as operators which take your current state to the next energy state or the previous energy state. So the higher one step higher or one step lower. Okay. So this is in terms of our simple harmonic oscillator. We can have same ladder operators. Instead of energy, we can have the same for angular momentum as well. Okay. So the ladder operators here, j plus minus, will essentially take you to the next angular momentum. Okay. So these are called ladder operators because they just take you to the next state. Okay. Okay. Yeah. So there is this property of these ladder operators that they commute with your j squared. Okay. Now, if I let's keep this aside. Okay. So first of all, let's go back to the question once again. What we actually want to do. So we are given that this gets j comma m. So j comma m. So these are the kets. Okay, these are eigenkets of total angular momentum. So if I operate j squared on this, I'll get this same state, right? I'll get this same state, but I'll also get an eigenvalue like this. And these are also eigenkets of jz. Okay, so if I operate jz on them, what will I get? I'll get mh cut and the same eigenkets. Okay. So therefore these j comma m are they are called simultaneous eigenkets of j square and jz. Okay. Now in the problem we have to show that if we operate these ladder operators j plus and j minus on these eigenkets, we'll get some other kets, right? So when we operate something, let's say consider this. Okay. What will this give us? This will also give us some ket, right? And we have to show that this ket that we are getting that this is also an eigenket of j square with same eigenvalue. So essentially, if I do j square on this ket, I should get j plus 1 and this same ket. Okay, this is what I want to prove. Okay, where this empty ket that I have drawn, the symbol of empty ket, stands for this j plus j comma m and also j minus j comma m. Okay, this is what we want to achieve. Now if instead of this empty brackets, let me put back this thing in, what will I get? I'll get j squared and j plus j comma m right? I'll get this thing. So what will this be equal to? Because we know that this j squared and j plus commute, so I can write this as j plus j squared j comma m, right? Why? Because they commute. So j squared j plus is equals to j plus j squared, right? So using this relation, I have written this left hand side as right hand side. Okay. So now, okay, we already know what this gives us. So this is, let's say, first equation here, this equation. From this equation, we know that this will give us just some j times these values. Okay, so this will become j plus and j plus 1 h cut squared and j comma m. Okay, so then finally I can rewrite this equation. So let me again write the left hand side. J squared operating on this ket j plus j comma m. I can write this as, so this thing will just, this is just some number j times j plus 1 h cut squared, and again I can write j plus j comma m. Okay, now we look at this equation very carefully, and what we see that if this is some eigenket j plus times j comma k m, and if we operate this operator j square on this state, we get the exact same state back, and also the eigenvalue that we get, they also do not change. Okay, so they are also the same, and that is what is given in the question, that this state j plus comma j comma m, this is an eigenket of j square with the same eigenvalue. Okay, so this statement is true. We can do the same for j minus as well, because j square commutes both with j plus and j minus, so there will not be any change, right? All the calculations that we have done, they'll remain the same. Okay. Any questions?
Okay.
Okay, so let's move on. Okay, so they are saying that there is an operator A, we have an operator A which satisfies this equation, and they are asking if A is an observable. When is an operator observable? How do we check it mathematically?
Expectation value, maybe.
Yeah, but there is even more simpler way.
Hermitian or not?
Yeah, Hermitian or not. Yeah. So basically, if A is an observable, essentially what the question is asking, that is A Hermitian. So, and it, because there is that theorem which proves that if you have an operator which is Hermitian, so its eigenvalues will be real. So if we can just show that our A is Hermitian, that will automatically mean that the eigenvalues corresponding to it are real. Okay, and vice versa. So we can show either of those things. So today we'll show both of those things, right? Essentially also proving the theorem. Okay, so what is the equation? It is a quadratic equation, a square minus 5a plus 6. a squared minus 5a plus 6 equal to 0. Okay, let's write in terms of lambda, if where lambda are the eigenvalues, so we get this equation. So what are the roots of this equation?
2 and 3.
2 and 3. So lambda is equals to 2 or lambda is equals to 3. Okay, so let's say this is lambda 1 and this is lambda 2. So we have two roots. Okay, so these are real eigenvalues. Right? These are real eigenvalues. And if we form the matrix of this operator, it will look something like this, right? And its corresponding eigenkets will be 1 0 and 0 1. Okay, this will corresponds to, okay, so basically if you operate A on this matrix, we'll get 2 times the same thing, and if you operate A on this matrix, we'll get 3 times the same thing. Okay, so these are eigenvalues and these are eigenvectors. Also you can see that if we take the adjoint of this matrix, then that will be same, right? Because we only have the real numbers inside, there is no imaginary part. So this is Hermitian. Okay, so the problem was solved here to this part itself when we got real eigenvalues. But essentially what we can do, we can write this operator as a matrix, we can find the eigenvectors, we can do all the things that we want. Okay, but for problem this much was enough. So is A an observable? Yes. Okay, pretty straightforward problem. So let's move on to the next one, and then we can take one quick 2 minutes break.
1 minute, one
Yeah.
very tricky problem. Can you go to the previous question?
Yes.
Yeah. You wrote this lambda square minus 5 lambda plus 6 is equal to 0 from the given equation. Can you explain how do you write this equation in terms of lambda? You simply replaced a with lambda. Operator a square minus 5a plus 6 is equal to 0, na? So you wrote it, you simply replaced a operator with lambda.
Right, I did actually. Okay, because what I assumed is, okay, there is an assumption. I can do this thing if I consider that my A is of the form this.
So you're assuming it is a 2 by 2.
Yeah, because it's a quadratic equation, so I know I'll only have 2 eigenvalues.
Okay.
Okay.
Okay, then.
So because now A is diagonal, so my A squared will just be this.
Okay.
Right? So then I can essentially, what I can do, I can write out for individual lambdas, right? These equations. So what will I have? We'll have this equation: lambda 1 squared 0 0 lambda 2 squared minus 5 times lambda 1 0 lambda 2 and then plus 6, which is just identity, right? So 1 0 0 1 like this. And then I can add individually So what I'll get? Lambda 1 squared minus 5 lambda 1 plus 6, 0, 0, lambda 2 squared minus 5 lambda 2 plus 6. And this is equals to 0. So this term has to be equals to 0 and this term has to be equals to. So instead of writing them separately, I have just written one equation because both of them are same equations essentially, right? This is written in terms of just lambda 1 and this is written in terms of lambda 2.
Okay.
Okay?
Thank you.
Okay, so should we move on then?
Yeah.
Okay, good. So, okay, let's move on to the next one. Now, we have previously also, we have solved some problems related to the concept of parity. Okay, and then today we will apply that concept and find out which of the following integrals are non-zero. So we are given these 4 integrals and we have to tell which are the finite integrals that are non-zero. And it is given that the functions in the integrals are hydrogen-like wave functions. Hydrogen-like wave functions. Okay. So this S is your spin, X is your X, and P is your momentum. Okay. So X is like position. Okay. Now how? Okay. What are the basically the prerequisites of solving this problem? So one thing is we should know what parity does. What parity does. So parity essentially takes us from x to minus x. And secondly, so when is an integral, let's say some integral f of x dx, when is this integral 0? When we have limits, let's say minus infinity to plus infinity. Okay, right. So when is this true? This is true when f of minus x is minus times f of x, right? So is okay when any function fx satisfies this condition, is it an odd function or is it an even function?
Odd.
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 Correct. So essentially now we will combine these two things. Okay, so they are asking that this integrals has to be non-zero. So whatever we have inside the integral must be even. If this entire thing, if this comes out to be odd, then we know that we'll get 0. Okay, and this integral, you can see the options, it comprises of 3 things, right? We have 3 terms. So for example, for the first one we have spin, we have this x, and we have p of 5, and all of these 3 will go into this integral as one single multiplication, right? Now one more thing. Okay, so what is even times odd? Is this even or is this odd?
Odd.
Yeah, this is odd. What is odd times odd?
Even.
This is even. And even times even is even. So there we have it. Okay, now I think we are fully prepared. So for the first one, if we apply the concept of parity, so under parity, is S even or odd? So as to say, will S go to minus S or will S remain the same? If it goes to minus S, then we say that it has an odd parity, or if it remains the same, then it has an even parity. So it is 2s x 2 pi. So we have this thing. Okay. So what is the parity of the first term? Even or odd?
Even. S has even parity.
S has even parity because it has nothing to do with position, right? The spin, either it's in plus direction, plus x or minus x, doesn't matter. S has even parity. So this is first term is even. What about the second term x? Does it have?
Odd.
Yeah, this has odd. And similarly, py
It again odd.
again odd. So these two odds will multiply and give us an even parity, right? And then even is again even. So the total parity, so this function in total, this is an even function, right?
How is py odd?
Because this we already solved one problem, if you recall, 2-3 sessions back. How do you write the operator py in terms of derivative? Do you remember? Iota h cut. You don't remember? Okay, anyway, it's iota h cut del by this thing, right? So if your y goes to minus y, because you have this derivative, right? Because of this derivative, you will also have a minus sign coming in your py. Therefore, it has an odd parity. Understood?
Sir, but that thing is related to the momentum, the
Hmm.
formula you wrote right now. But aren't these referring to these orbitals S, comma P, D,
No,
those
no,
sort of?
no, no, no. These are not orbitals. These are not orbitals. So this S, okay, I should have clarified. This S is spin. Oh no, you are correct actually. My bad. These are in fact orbitals because here they have given D. Okay, anyway, doesn't matter. For orbitals also we have the same thing.
I
Okay.
think because S is a spherical symmetry, so I
Yes.
think S is a even one, and P being the dumbbell shape, maybe that is the odd parity.
Mm-hmm. Yeah, yeah. Let me quickly check.
Dumbbell is also even, isn't it?
Mm-hmm. Okay. Yeah. So these are orbitals. I have misread the problem. Okay. So when we have orbitals, so all of this thing remain the same. Okay. Whatever we have discussed about these integrals and all these things. Okay. Then what we do for orbitals, it is very simple to calculate parity. So what we do, okay, for s, when we have s orbital, okay, so let's first write down that we have these values L, right? So the values of L 0, 1, 2, so on, right? And these corresponds to our S, P, D, so on. Okay. So the parity of any orbital is just minus 1 to the power L. That's it for orbitals. Okay. So minus 1 to the power L. So for S, L is 0. For S, L is 0. So it has minus 1 to the power 0, so 1. So it has even parity. P will have odd parity. and D will again have even parity, and so on. So odd even continues. Okay, so now let's go back to the problem. Let's solve it here only. So this is S is even and X is always odd and P is also odd. Oops. P is also odd. So which means this odd will give us even and even. So in totality this is an even parity. So this integral is non-zero. Okay. For the second one, this is even and this x square. Now notice that we don't have x anymore, but we have x square. So x square is even and this is odd. So what do we get this time? We get
Odd.
odd. So this integral will go to 0. What about this third one? Odd, even, odd. So we have two odds which will make an even and then we have one even. So this is even. So this integral will be non-zero. What about last one?
Odd, odd, even.
Odd, odd, even. So in totality,
Even.
even. So again, this is non-zero. So A, C and D. Okay.
Can
Now,
you elaborate on the parity of the orbital? Why is it minus 1 to the power L?
uh, okay, so before that, I'll just like to quickly mention because this came up that they have dumbbell shape or this thing. But notice that they are probability density clouds, right? Where we are taking mod square of these things. Okay. So they are squared and they are not just the pure vitals, right? This, not the wave function. These are wave functions. Okay. They are not the probability distribution. So for probability, what we generally plot is the dumbbell shape and all these shapes. So for example, for p orbital, we plot this thing, right? Where we take the mod p square. Here it is only just the p,
Wave function.
only the wave function. And if you look at
This
the
wave is negative and half is positive. You mean to say
Mhm.
that?
If you look at the hydrogen atom wave functions,
Uh-huh.
there itself you will see that when you're from there itself you can see that when you have these L as even numbers, that you will have an even function, and when you have these odd numbers, that you will have an odd wave function. Okay.
Okay, got it.
So it comes from the wave function of our hydrogen atoms.
Okay.
Okay, so my apologies for misunderstanding the problem and thank you for the correction. Okay. So let me quickly take a small break and then we'll continue. Meanwhile, you can try to solve this problem.
Will it be 3 by 5? Varna,
Yeah.
will it be 3 by 5? This one. M is equal to 1. The probability of measuring LZ.
अच्छा,
This,
आप इसी क्वेश्चन की बात कर रहे हैं?
हाँ. इसलिए ना, see
हाँ,
about this LM.
ये जो आगे वाले हैं ये मेरे को नहीं याद, क्योंकि मैंने अभी हाइड्रोजन एटम तक नहीं मैं पहुंची हूँ। मैं तो अपनी जो बेसिक नॉलेज है उससे कर रही थी सॉल्व।
नहीं, आई एम ऑल्सो इंट्यूटिवली सेइंग बिकॉज अगर ऊपर का देखोगे ना y1 -1, so it is LM. So L is 1, M is -1, then L is 1, M is 0, and then L is 1, M is 1. So M
राइट।
is equal to 1 is the last term.
हाँ।
So I'm just taking the square of that. Those other terms don't have M is equal to 1. So
measuring LZ.
that's fine. Just making a guess.
Okay. So, okay. So could you solve this?
Mana, will it be 3 by 5?
Yes, 3 by 5. So, okay. I hope we have figured out the trick that they are asking with m is equals to 1, and there is
Yeah.
only one term that have m is equals to 1. The other two terms have m as -1 or 0.
But the only thing that how is it the probability of measuring LZ? How is it connecting with LZ?
Okay. So, for example, in the previous problem, one of the problems on angular momentum, here. So when we write these wave functions as j comma m, or the wave functions given in this current problem, so they are simultaneous eigenkets. So they are simultaneous eigenkets of two, like j squared, in that problem it will be L squared,
Yeah.
and jz, in that problem it will be Lz. So j squared, when we have j squared, we get these eigenvalues.
Mm-hmm.
Notice that they depend on j, and for jz we get m h cut eigenvalues.
Mm-hmm.
Okay, so coming back here, because they are talking about Lz, so its eigenvalues will correspond to m. And if they talked about L squared, then the eigenvalues will correspond to LL plus 1.
That will be the eigenvalue. So here, what will be in case of L square? It would be what? L is 1, na? L
L
is
is
1.
1, L is 1. So this is simply 2. Yeah.
But this is the given is psi. Psi is a wave function. So from wave function, how are we calculating the probability of the angular momentum z component?
Yeah.
Lz.
So you notice that this is written in terms of y, right?
Yeah.
This y.
Y L.
Where have you seen this y?
This is हाइड्रोजन एटम का जब
Yeah.
करते हैं.
Yeah. So this YLM,
Uh-huh.
they are called spherical harmonics, right?
Yes.
Spherical harmonics.
Yeah.
And the question just assumes spherical harmonics. The question just assumes that the reader is aware of this notation,
Mm-hmm.
and
Okay.
just looking at these y's, he'll understand that okay, here we have 1, 1, 1, and -1, 0, 1. Okay, so we have angular momentum, so L is 1, and corresponding to L is equals to 1, we will have 3 values of m, right, from -1, 0, and 1, right? Correct?
Uh-huh. Okay, because these are spherical harmonics, so they are directly related with the angular momentum.
Yes, so
That's
L is
right.
equals to 1 corresponds to our p orbital, right?
Yes.
And these three then let's say are px, py, pz.
PZ. Okay.
So our total wave function, this is written in terms of px, py, pz. Okay?
Yeah.
And then
Okay.
they're asking what is the probability that we are measuring pz, right? M is equals to 1. What is the probability? So the last term we know corresponds to pz, and they are asking that what is the probability that we are measuring that state.
Okay.
So
Got
one thing again, we should always check if the wave function is normalized or not.
Right.
So if we add the coefficients, this will be 1 by 5 plus 1 by 5 plus 3 by 5, which is 1, right? So it is normalized.
Yeah.
Then we can directly say that the probability of measuring LZ with m is equals to 1 will be just mod this C3, which will be the third coefficient squared. Okay, this is our probability, and this is nothing but 3 by 5. Okay, or
Yeah.
0.6. Okay, clear?
Yeah.
Okay, so then let's move on to the next one. So, okay, this is one problem based on particle in a box, which just, I don't know why it is being kept here, but it's good. We'll have some revision of particle in a box. Okay, so what are we given? We are given two non-interacting identical particles. Okay, we are given that they are confined in a two-dimensional, okay, both of them have mass m, and they are confined in a two-dimensional box of sides A. The energy of the system in the state psi 2 comma 2 and psi 1 comma 4 will be this thing, and they want us to find out n. Now can you please tell me what is the meaning of psi 2 comma 2 x1 y1 and psi 1 comma 4 x2 y2? What do these subscripts mean?
These are the n and m values.
Yeah, these are the n and m values. If you recall, okay, so this is a two-dimensional box, right? This is a
But
2D.
M4 is possible. M4 means
Okay, okay, let me write. So, okay, we'll solve this, and then I think it will become clear. So for two-dimensional box, we'll have two coordinates, right? X and y. Instead of just having x, we'll have x and y. And the energy of a particle in a 2D box, how do we write it? We write it as pi squared h cut squared upon 2m a squared, and one we'll have for x and one we have for y, or sometimes we also write n and m. Okay, n or m, or you can write nx and y. Okay, so this is energy of one particle. So this is the wave function given for the first particle. Note that it is x1 y1, so this is first particle, and here we have x2 y2, so this is second particle. Okay, so now for particle 1, what will be the energy? For particle 1, what will we have? Now here this 2 comma 2 means our nx is 1 and ny, sorry is 2. Nx is 2 and ny is 2. Okay, so the energy of our particle 1, let's say E1, this will be 2 squared 4 plus 2 squared, which is again 4, so 8. Okay, so this will be 8 pi squared h cut squared over 2 m a squared. Okay, similarly for particle 2, here nx will be 1 and ny will be 4. So the energy, so this thing will be here, so 1 squared will be 1 and 4 squared is 16, so we'll have 17 pi squared h cut squared over 2 m a squared. Now for total energy, we can just add these two, E1 plus E2, and we'll have 17 plus 8 is 25, so we'll have 25 pi squared h cut squared over 2 m a squared, and 25 is square of 5 squared. Okay, now if we compare if we compare with the energy of the system that is given, it is written in terms of capital N square, and they want us to find the value of n. So the function that is given to us is this, and we can directly compare and see that n is 5. Okay, now now you can ask what you are asking.
But if the particles become interacting, when are the particles non-interacting and when do they become interacting?
So here they are non-interacting, so we can directly write this thing.
Yes.
If they were interacting, then we also have to take into account the interaction energy. Okay, for example, they might attract each other, then there will be some
The
negative
Coulomb
energy that will
attraction
come.
repulsion.
Correct, right. So because whenever we have some attractive force, that corresponds to some negative energy. If they repel each other, then we will have some positive energy. Basically any interaction energy that comes, positive or negative, doesn't matter, that we also have to take into consideration when we write this total energy E. Because
Okay.
they are non-interacting, we can just simply add their individual energies, because the interaction energy is 0. Okay, so if no doubts, then let's move on here. Okay, so we have already talked about these operators, and this is how they are defined. Okay, so I already mentioned briefly what is their role. So this is called a creation or raising operator, a dagger, and the second one is called the annihilation or the lowering operator. And notice that here they have defined them in terms of x, which is your position, and p, which is your momentum. Okay, so we can do this thing. Now they are asking what is the value of the commutator a and a dagger. Yeah, so this is a very standard commutator, so mostly everybody knows it. But we can also solve this explicitly. Okay, so what is, okay, let's solve this. If I write a comma a dagger, I can expand this and write this as a times a dagger minus a dagger times a. Okay, so let me just focus only on the first term for time being, which is a dagger, and these two are given to me here, okay, in terms of x and p. So my a times a dagger will become m omega by 2h cut times x plus iota times p. Okay, and this thing multiplied by a dagger, which is essentially the same thing, half x, and now here I have a minus sign. Okay, so this is a comma a dagger. Now, so these first two terms will give me x squared, right? This term and this term, they'll give me x squared. Similarly, these last two terms will give me p squared, and then I'll have two cross terms. So this and this will have xp, and this will have px. Okay. So if I simply write it down, this becomes m omega by 2 h cut, and this square and half cancel each other. This becomes x squared. Similarly, I have, okay, this is iota and minus iota, which means minus iota squared, which is plus 1 to m h cut omega, and this will give me p squared. And then if I multiply this with this thing, so notice that this m omega and m omega, they cancel each other, and what we are left with this is iota by 2 h cut. So what we are left with is this minus iota by 2 h cut, and this will give me xp, and similarly this other term will give me minus px. Okay, this term. Okay, now what is this?
IH cross.
Yes, so this is just the commutator of x and p, and we know that this is equals to iota h cut. Okay, good. So this h cross will cancel out with this, and we're left with iota squared, which is minus 1, so this will become plus half. Okay, so this entire thing basically, let me write this thing again. Let me do one more thing. Let me take out this thing outside. Okay, because if I do this thing, then this second term I can write it as p squared over 2m, right? And then this first term I can write this as m omega squared x squared by 2, and then this is simply plus half. Now what is this thing?
Hamiltonian.
This is the Hamiltonian. This is the kinetic energy, this is the potential energy. Good. So what we have the Hamiltonian, and we have divided by h cut omega, and we have this thing plus half. Now what difference will we have if instead we do a dagger a? What will we get? So doing a dagger a, okay, I'll just make the changes here.
I
Instead of
think that
plus
will be
sign,
same. It will be same, I suppose.
just one minor change. Here it will be minus half.
Minus sign, yeah.
Yeah. Okay, so you can see easily. So here instead of minus, and this will be plus, this will become minus. So these two, they'll remain the same. And what will that do is that this will become minus xv, and this will become plus px. So this negative sign outside will become positive, and then because we'll have this iota squared, that will make it negative, so we'll have minus half. Okay, so this is essentially the same thing, but we'll get a minus half. Okay, if you want, you can do the calculations yourself. It's just the same, you just have to change the sign, no big deal. Now what we wanted to do, we wanted to find out the value of this commutator. We have a dagger, we also have a dagger a, right? So we have to just subtract these two. Okay, so if I subtract, what will I get? So this h cut, so this first terms, they'll just cancel out each other. So let me write here, so a comma a dagger, so this will cancel out each other, and we'll have half minus minus half. which is 1. So a comma a dagger is 1. Okay, which means option D. Okay, any doubts? No? Okay, so that's it for today's question, but I have a few more if you want. If you want to ask anything that is there, that also we can do.
Sir, in the first question,
First question,
that first question,
all the way up here. Yes, first question. Yeah.
this one, I do not know the derivation for this one, spin operators.
Okay. Um, this one, that this cyclic relation, that
Yes,
this SZ comma SX, that this will equal to iota h cut, sorry, iota h cut SY. Are you talking about this?
yes.
Okay, we can do that if you want. But I think, so is this not discussed in the lectures? I'm not sure.
Okay, okay. If it's in the lectures,
I'm
then
not sure. I'm
never.
not sure. If you want, we can do it. Yes.
The eigenstates of A and A dagger operator.
Yeah.
I have three questions.
Yeah.
So
Yeah.
maybe one. Yeah.
Yeah. We'll do that. Okay. So, uh, have you been taught about Pauli matrices in the lectures?
Yes.
Oh, okay. Then it's good. Okay. So then let's do it. So we define these spin operators in terms of Pauli matrices, right? So let's say any Si, that will be just h cut by 2 sigma I. Okay, where sigma x is 0 1 1 0, sigma y is 0 minus iota 0, and sigma z is 1 0 0 minus. Okay, now let's say we want to prove the cyclic relation for Sx and Sy. We want to prove this relation, let's say. Okay, so we can write this commutator as Sx Sy minus Sy Sx, right? So this becomes h by 2 sigma x, so h cut by 2 sigma y minus h cut by 2 sigma y and h cut by 2 sigma x. Okay, basically h cut squared over 4 commutator of sigma x sigma y. Okay, now this sigma x, sigma y, let's multiply. So 0 1 1 0, 0 minus iota plus iota 0. So if we multiply this, what do we get? So this first term will give us iota 0 0 and minus iota. Now if you compare, this is same as sigma z but with an extra iota. So I can write this as iota times sigma z. Okay. Similarly, I can find out this thing, sigma y, sigma x, and this will come out to be minus iota times sigma z, doing similar multiplication, just the other way around. Okay. So this commutator sigma x comma sigma y, this will be 2 iota sigma z. Okay. This commutator, this will become 2 iota sigma z. Okay. So what our Sx comma Sy becomes then, let me write it down. So our Sx comma Sy, this becomes h cut squared by 4 multiplied by 2 iota sigma z. Okay. So let's take iota h cut outside, and this we can write as h cut by 2. And what is this? This thing?
That is Z.
Yeah. So iota h z. So essentially we have proved this relationship. Now you can do the same thing for Sy Sz and you will get Sx, and you can do for Sz Sx, you will get Sy. Okay. So there is this cyclic relationship that if you have x and y, you get z. If you have y and z, you get x, and if you have z and x, you get y. If the order is flipped, you will get an additional minus sign. Okay.
Can you scroll down a little bit?
Yes.
I'm just wait.
Okay. Any other doubts? Harshul?
Uh, this, this.
So if you if you are unfamiliar with Pauli matrices,
No, I'm familiar.
okay, then
I
it's fine. Yeah, I suggest that you watch the lectures. I think these are discussed in the lectures. I'm not sure about the cyclic relationship, but these Pauli matrices are there for sure.
okay, okay.
Okay. Any other doubt that you want to ask?
I have doubt in the tutorial question.
Tutorial question. Which question? Or the assignment question you want?
Not the assignment. They share 5 problems every week, right? Tutorial. 2 videos are released along with the lecture videos.
Okay, I'm not aware. Oh, okay. What doubt you have? You can ask.
Uh, but for that, I need to share my screen.
Okay. Share share your screen. Is it not allowed?
No, sir, not allowed.
Okay.
I have to be given permission.
Let me change the settings. Okay. Now try. Can you share now? Yeah, you can see your screen.
So this is the first problem. Consider a system of
Yeah, I can see it. So you have doubt in the first one?
yes, the first one.
Okay. Okay, so I'll just give you a hint and then I think you will be able to solve on it on your own. So it is a similar problem that we have solved today, right? It is a two-dimensional box. We have two non-interacting identical particles and we have to find the energy and the wave function of the ground state of the systems. Okay, we have two states, fermions and bosons. Assume both the particles are in the same spin state. So when we consider them to be fermions, what do you think will happen?
They are attractive. I mean, minus sign will be there in the wave functions.
No, because okay, so first of all, they have clearly mentioned that they are non-interacting particles. Okay, so
Okay,
so
okay,
they will not interact. So
okay, sir.
what then? If they are fermions, then what do you think
The
will be the difference?
Pauli's exclusion principle has to be followed.
Yes, exactly. So we have to follow the Pauli's exclusion principle, and that principle would suggest that both of the particles, because they also have the same spin state, so they cannot have the same spatial state, meaning both of them cannot be in the same ground state. Okay, whereas when you consider them to be bosons, both of them you can consider to be in the same ground state. Okay, so if you remember, we had nx and ny, right? When they
Yes,
are
sir.
bosons, we can take nx ny as 1, and then again for the second particle we can take nx ny as 1. But if they are fermions, for one particle we can take them as 1 comma 1, but for the other particles we have to take them as 2 comma 1 or 1 comma 2. We cannot take 1 comma 1. That is the
That
difference.
I did not understand that part. In the solution also, they mentioned this thing.
Okay.
Fermions 1, 1, 1, 1, 2.
Ha ha.
The
See,
both.
see, 1 1 1 2, which means that your particle 1 has the n value, right? The nx value as 1, ny value as 1. But for particle 2, you have nx value as 1, but your ny value is now 2 because they are fermions. Do you understand?
Sir, this Pauli exclusion principle stating that one of the states has to be 1, comma 2, while the other one is 1, comma 1. This
Mm-hmm.
part, I I don't know. Is it that it's some sort of rule or something like that, or
Yes,
I
it is. It is some kind of a rule. So, like for example, in a hydrogen atom where we have electrons, right? And you know electrons are fermions. So when we fill the orbitals of an electron, can you put all the electrons in s orbital? No, right? Only two
no?
electrons go there. And that
Yes,
too, they should have opposite spins, right? They cannot have same spin. So the Pauli's exclusion principle is for fermions that any two particles cannot have all quantum numbers as same, right? So they cannot have let's say for here, how many quantum numbers will be there for a 2D box? You will have two quantum numbers, n and m, or nx and y, right? Two quantum numbers. So because
Yes.
they are fermions, you cannot have same quantum numbers for both the particles. If you assign 1 comma 1 to first particle, you cannot assign 1 comma 1 for second particle as well. That will violate Pauli's exclusion principle. Okay,
Right, sir.
right.
So
So therefore you
that's
will have
why.
to take 1 comma 1 for particle 1 and 1 comma 2 for particle 2, because that will be the next lowest possible energy. If you take 1 comma 3, then that will not be the minimum energy state, right? That will be even more excited state. And because they are asking for the ground state energy, so for the ground state, what we will have? We will have particle 1 will have 1 comma 1, that is the minimum possible. Next minimum possible energy will be 1 comma 2.
And one more thing is, sir, here they came up with this wave function for fermions, antisymmetric, and for bosons, it's symmetric, they told.
Yeah, this is like this is okay for a fermion. The wave function always has to be antisymmetric, just like fermions follow the Pauli's exclusion principle. So it is, again, it is like a rule. Okay, and you can prove this thing. So okay, so this thing can be proved, that for a fermion the wave function will be antisymmetric, while for a boson the wave function will be symmetric. We can prove this thing. Okay, you can look up for this proof and you will find it easily. Okay,
Okay, okay,
okay,
yeah, that was the
okay, done. Okay,
yes, sir.
okay, then you can stop sharing and I'll share back. Okay, so I think we don't have much time left, so we'll just discuss a couple more doubts that ma'am had. Yes, so ma'am, can you please repeat what you wanted to ask?
The eigenstates of A minus and A plus operators, the ladder operators.
The eigenstates or the eigenvalues?
Eigenstates. Eigenvalues will be n. Is it?
Okay. So, okay, are you familiar with this notation when we write our this thing as n, the any state of our oscillator or something?
Nth state, right?
Nth state,
Nth,
yeah.
nth
Yeah,
state.
yeah, yeah. So, as I also mentioned briefly, let's say we we do this raising operator. Okay,
Mhm.
we operate this raising operator. So what will we get then?
We'll get this will be under root of n plus 1 into n plus 1 eigenstate.
Correct. So this thing,
N plus 1 eigenstate.
yeah. And similarly for the lowering operator,
Mhm. This will be under root of n and
yeah,
n minus 1.
yeah.
Yeah.
So what is your doubt then?
How to find the eigenstate? This is not an eigenvalue equation. This is not an
Okay,
eigenvalue.
okay. You want to find out the eigenstates.
Yeah.
Okay.
What would be the eigenvalue equation for this? For A plus and A.
Okay. Okay, that thing I have to check.
Okay.
I cannot recall right now.
Okay. Okay. Maybe in the next class.
Yeah, sure, sure. In the next
Yeah.
class.
And the other was how to derive psi n x, psi n x,
Psi n x,
and
like this.
the equation is equal to psi n x is equal to ket of sorry bra of x, bra of x
This
and
one.
cat of n. Yes, yes, yes. How
Ah,
do we
okay,
get?
okay.
How do we get this?
Okay, so what we have here? We have a wave function which is a function of x, right?
So actually, ma'am said that from here we can derive the expression for psi naught, and then we can find psi 1 in terms of psi naught, and then psi 2 in terms of psi 1, and so on. So, but for psi naught, if I can get something from here and then proceed.
Sorry, I did not understand.
Okay, okay, you start with this. I'm sorry, you start with this.
Okay, so this is uh, okay. This is like more like Schrodinger's picture, right? And this is more like what we say
Isaac?
Heisenberg's picture.
Okay.
Okay, so when we have a cat, right? When we have a cat and
This is the nomenclature. So you said this is a nomenclature
this
to
is a
write.
nomenclature.
Okay. And then she said that psi n of x0, psi n of x0
Psi n of x
is
0,
equal to bra of x0,
bra of x 0,
then right, then a plus dagger to the power n,
a
a dagger
a dagger
the
to the power n.
power n, divided by n factorial under root,
Yeah.
and then cat of 0. Yes.
Okay.
And then solving this equation, she found some differential equation, and then integrating it, we
So
got
I
an expression
think
for.
I think it should be x here, but 0. Oh no. Okay. I think it should be just like this, and also like this. Is this okay? I
Okay.
don't know why there will be some x 0.
Okay.
I think this is the equation.
Okay.
Okay.
No, but then this 0 cat, how
Hmm.
do we get 0 cat? No?
So 0 kit. Okay. In this nth state, 0 kit basically this means ground state.
Okay, okay. Okay, then you operate it n times and then you get the n.
Yeah. Yeah,
Okay, okay, okay.
yeah. Okay.
Okay.
And then what this basically does is this is like a transformation from your. So this is like a ket space, right? Where we are just saying
Mm.
this is the nth state, and
Right.
we want to go to the. This is like a x space or the kind of a real space, right?
Mhm. Mhm.
If we want to, if we want to go from ket space to a real space, we have to perform this operation.
And can from the lower equation, can we get an expression for psi n x in the Schrödinger picture using the right hand side? Maybe we put a dagger and then you solve the differential equation.
Okay, so okay, let me simplify it a little bit. So first of all, this is the equation. We start
Okay,
from ground state.
okay.
We start from ground state, and
Hmm.
we can go to any nth state by raising the ladder operator n times. And
Right,
this factor comes for this normalization thing,
right.
right? Okay, so this is
Okay.
one thing. Now I can substitute this n directly in this equation, right? The one that you have mentioned above, and you see
Hmm.
that I am getting the same equation.
Hmm.
Okay. Now what this means is, so there are two things. One is that how do you get from ground state to any nth excited state? Okay.
Hmm.
So you can write any nth state in terms of ground state by using this operator. And then you can go to the Schrodinger or the real space kind of thing if you do this small change that you take a bra x and then ket of n. Okay, that's it. So we have two things. One is that we are going to the nth state, and then second thing that we are going to the Schrodinger like wave function psi n of x.
Hmm.
Okay.
If I take n is equal to 0, then will I get the
Sorry,
expression for
if you take what to be 0?
n is equal to 0?
Yeah, if you take n is equals to 0.
then can we obtain the expression for psi naught, which is the ground state wave function for the for the harmonic oscillator?
So n is equals to 0 essentially corresponds to our ground state, right?
Ah, right. So expression for psi naught x, using this expression, how to evaluate?
Huh, that is not there. That basically we cannot do. We must know this state. Once this state is known, then we can write all this. So one thing that we okay, so there are like couple of ways of doing that.
Mhm.
One thing is that we know we cannot go lower than our ground state.
Mhm.
So if we operate this the lowering operator on 0, we know we should get 0.
Yeah.
Okay, we know
Mm.
we should get 0. And the other thing is we solve the Schrodinger equation for the ground state.
Mm.
Okay, and then we find out the wave function.
Mm.
But there is no using just this we cannot get the ground state wave function. See, the problem is if we okay, if you let's say if you want to find out, if you don't consider the raising and lowering operators,
Mhm.
then finding the higher order wave functions for a harmonic oscillator problem is very non-trivial, right? You have to consider Bessel functions or some Hermite polynomials or something.
Okay.
But finding out the ground state wave functions is trivial, that you can do very easily. And using this raising and lowering operators, they make our job much easier, that we can just operate this thing and we will get the higher order wave functions. That is why we use them. So we by using them we bypass all the mathematical this nonsense that otherwise we would have to tackle.
Okay.
Yeah. So they just make our life easy. That's it. But using this, you cannot find out the ground state wave function. You can do that by using this equation, but not without. I mean that is essentially same as solving the Schrodinger equation for the ground state.
Okay.
Yeah. Okay. So this one I'll discuss in the next class.
Okay.
I don't recall as of now how to find out the eigenstate of this ladder operators. Okay, so I think it's time, and then we'll meet on next Saturday.
Thank you.
Thank you so
Okay,
much.
thank you for joining. Have a nice evening. Bye bye.
Bye.
Bye bye.